you. So welcome everyone to this tutorial session on automating control horizon. So we are quite excited to share with you the finding of the IFAC Industry Committee about innovation and automatic control and technology transfer to in an industrial setup. So let me start with detail about innovation that took place approximately in the 18th century in Central Europe. So you can imagine that the 18th century in Central Europe was a time in which the first automata started to be invented, and people were playing with this idea of automation, right? So imagining machine and device that could do things on their own automatically without actually human interaction. And it was really a primordial state. So there were just mechanical automata system, and this was more or less the trend. So this is what you could smell in the area, but was of course very far away of being something more concrete and advanced. So during this period, one interesting device came about called the Turks, was an automaton. So in principle was like a robot, so was presented in show and theater as a robot that was able to play chess. And actually was considered quite strong, right? I mean, he played against professional player. Historically, it seems he even played with Benjamin Franklin. And it was amazing, right? It was really what we would see today as science fiction at the time. So what happened is that in reality, it was a trick. So there was actually a person inside that was like well hidden, and this was a professional player that would just then move the robot and determine the next step of the game. So people would see this, be amused, and move on. But somebody that was actually the great-grandfather of computer science, Charles Babbage. So Charles Babbage was an engineer, as a mechanical engineer. So of course was fascinated and was playing himself with the automation and knew very well that this was not possible at the time, right? So the technology was not there, the trends are there, but the technology was not there. So one thing he did that made a difference from there on was that besides stopping and being amused, it said something like, okay, what would it take to make it happen? You know, so where are we now? We are clearly not there, but what do we need to do? What would be an elegant way, an elegant solutions besides just hiding somebody inside to play the game? For that this could happen. And this is where, like, several years afterwards, he started to move the technology towards developing the first computers. So this way of thinking is what we can think about within today's framework, for example. So let's move in today's century. If we look at the current technology and societal trend, we are still looking into automation. So more automation, faster automation, better automation. And of course, also electrification and digitalization are in the air, so to say, right? So those are all things that we are all working on and aiming for in our daily life. And also from the societal point of view, we are looking more and more into sustainability solutions. So we are starting to discuss things like, okay, are our solutions sustainable for the next 10 generations in terms of energy, resources of various types? So if we had to think about ideal vision nowadays, right? And envision an energy efficient society and cities, we can imagine things like what would it be to have infinite energy resources? Like what would it be to have, for example, harvesting energy from the sun with 100% efficiency? So what would it be to be able to have a process that runs completely automatically and will not break overnight. So it's all this kind of thought that then push all of us to say, okay, what are we missing yet, right? How can we push the technology to the next level and realize this vision? So focusing now on control. So those are like general trend in our engineering society, focusing now on control and looking where are we now. One of the things that is probably particular about the control community is that we have at the moment a big dichotomy between what is effectively in place and what are we studying and developing technology for, right? So on one hand, we have here on the left, let's say the academic community, the fundamental research community that has been doing enormous step in the last several decades. And on the other hand, we have industrial applications. So you can think about automotive, but also industry, production, robotics, where in the majority of the case, we still have things running on PID controllers, right? So it's a huge gap. On the other hand, if we think about where we would like to be, there are existing technological trends and push to do more from the process and product side. So things that the people working on in industry application wants to see on their product. So the question we asked ourselves is, okay, how can we develop an agenda, like an applied research agenda, that could in principle be aligned with those trends, right? But also be aligned with this real world like trend and solution that we want to see on our product. So if we look a bit more in depth into this cradle of innovation, we call it, like it's an innovation cycle that collects the academic and industrial reality, we see three things. So on one hand, we see the fundamental part of research, which include fundamental research, but also applied research, and also like in a research portfolio, right? Which is like a series of problems that we want to solve. Then, on the other hand, we have really the marketing. So people that use product and solution. So those are users, right? So not necessarily technical people, but users that look at what they want to see in their product for next generation. And all in between, we have, of course, like engineers of various disciplines that try to translate the system requirement specification into technical requirement specification. And finally, we have the engineer that make those things happen, right? Realizing. So the problem is that often things get blocked here. So they don't really go in the innovative part, right? So this cycle will start maybe with some of customer requirement specification that then go up to, in a healthy company, this will develop a technical requirement specification for the agenda of the development. And this then goes in develop, engineering, product management, and it. So the whole research part, so the whole opportunity, the whole potential energy of realizing much more is completely skipped. So you're going to have to think that here on the left, there is a huge potential of doing much more. But things get blocked. And one thing we did within the task force of the IFAC Industry Committee was really try to look and understand why things get blocked. And to do it, we contacted different industries. So we were in contact with different product management, but also, let's say, control specialists that work in the industry and try to understand, okay, why do things get blocked there, right? So what is the issue? And how can we unblock them? So to give you also another idea from the control perspective on how things are with respect to the industrial, like several of the industrial reality. So if we take the map of control theory, and this is by far not even complete, but if we look at the methodology that have been developed, and we look what effectively the majority of industries using now, so we are really at a very poor ratio. So one first thing was, okay, try to understand why this is the case, right? Why we are still running our reality in PIDs. So there were 4 key factors that we identified. One was the different KPIs, right? So the KPIs on academia would be publication in high impact journal and conference. So this is what academics need for their career, for their success. This is what's important for the community. On the other hand, industry KPI is mostly financially driven, right? Even on the hand, like they are all accompanied by the idea of we want to push innovation forward, but still these 2 KPIs are plays a bigger role. So they have a majority of the weight in terms of what it's requested by both community. The second aspect was time scale. So in academia, we can still afford playing with years, right? Brainstorming, having idea, tries creating idea. On the other hand, the industry is constrained by time to market. So time to market is crucial because a product going out of the market, even in an imperfect 80% status, is way better than 100% 5 years later, because then you lose the turn, and then you lose several hundred of millions on this. Other aspect is, of course, communication. So the reality of the academic communication is that it's open. I mean, we all join conference. We try to exchange as much as possible. We know that exchange is also what keeps us alive and what foster new idea for the community. On the other hand, I mean, industry would like to communicate. It's not that it's not done, but effectively there are way more constraints in terms of intellectual property protection, right? And here again, there are strict regulation by most of the company. finally, last but not least, the type of specialized knowledge that the reality has. So typically, the control community will have a very specialized knowledge on the method and some knowledge on the application, and vice versa, industry will have a very specialized knowledge on the application, and in some case, like a superficial knowledge on the method. So those are the factors that we identified, and then we'll be more in the individual talk. Here I just give you a couple of examples of how these gaps can be bridged. So on one hand, we have here, again, the cycle of innovation from research to eventually product. So one typical example we said where things get stuck is when we go to fundamental and applied research, and then we get the jump in development. So one tool, for example, that we identify were like digital twins, because digital twins are something that the company in development and engineering is used to test their solution, right? And to do fast prototyping. And the idea is, can we, from an academic solution, try to introduce this step a bit earlier? So could you already try to maybe create a small closed loop here between applied research, development, engineering, and then go back modifying our solution so that then it will fit better the development and engineering requirement? And another thing is that tools like this advanced simulation and digital twins then could also provide some kind of demonstrator that can be then used for the end customer, right? For marketing purposes also, or for push new solution. On the other hand, from end user to research applied portfolio. So here, it's fundamental to have, we say, translator, right? So people that are really willing to sit down and talk with product management and understand, okay, what are your problems? So what do you want for your next product? And then try to translate this specific requirement into technical requirement and then control problems. So I can give you one example from power conversion on this. So one typical specification could be the customer comes and say to ABB, like, I want a plug-and-play converter, right? I want a converter that now, with all the crazy things going on in the grid, but also the process requirements, or the industrial process requirements, I want to be able to put it there and adapt to everything. Then the control engineer would come and say, okay, so what can you measure? Like, let me know specifically what can you measure? Like, so voltage and current, for example, on the grid side, and then torque and speed on the machine side. And then you go, you can interpolate, and the point would be, okay, what would be a good nonlinear system identification that would provide parameters for a nonlinear model of the grid, for example, or the existing load. So this is to give you an idea of the kind of exercise that we try to do in the different discipline and really try to move on to a suitable solution. So what we did was we were a team of more than 30 people, actually, both from academia and industry. We put together an edited volume in which each chapter, you see the 6th chapter here, was dedicated to a different industry. So first part was on infrastructure and mobility. There was the data industry, building automation, automotive control. The second part was energy and production, was power conversion system with the BB, robotic and manufacturing automation that we'll hear today also from Efe and Alisa, and the process industry. So this exercise of the cradle of innovation was actually iterated in all these scenarios, and we had the opportunity today to listen to two of this talk, from one Alisa and Efe, and the other one for Peder. And then for the final part, also Tariq will give us an introduction to the control horizon roadmap for 2030 as well. So having said that, I would like to introduce our first speaker, which is Alisa. So Alisa is currently a professor, an endowed professor at the University of Applied Science in Zurich, and previously she was a group leader at Inspire. And for this work, she collaborated also with Efe, that was postdoc at the Automatic Control Laboratory at ETH, and is currently also leading a group, innovation group at the Inspire Institute.
Okay, so I'm going to talk about one of the chapters in this book, and my favorite topic, so robotics and manufacturing automation, especially how does that relate to industrial applications, and how we create actually methods which are inspired by industrial applications. And you saw the graph from Sylvia. So I will show you, and Efe as well, we will show you examples, concrete use cases on how actually real challenges lead to innovation and to valuable research. And in manufacturing and industrial robotics, the innovation drivers are two, the main ones. Industry 4.0 or 5.0 nowadays, and sustainability. And Industry 4.0, this is all about the availability of data, the computational tools that we have nowadays, and capabilities, and the connectivity in the cloud provide possible and enabling very much innovation. And that innovation translates into advanced functionality and in particular autonomy of the systems, so increased, improved decision-making capabilities and optimized production, which is very important for the industry. And talking about optimized production, previously this kind of optimization was very much motivated by economic performance indicators. Okay, how does that work? Okay. So economic performance indicators, and the technology development was very much centered towards this blue-green part that you see. But nowadays, more and more, it becomes important to think about emissions and environmental indicators and even societal performance indicators. And this means that our system should be not just faster, better, and more efficient in the standard sense, but also cleaner, and they should be adaptable. They should be producing just single parts and be able to self-diagnose and also be able to be operated remotely. And how to achieve this kind of adaptability, this is where our research comes into play. And if we put all this together, the big question is how can we build manufacturing systems that can produce this kind of single batches, so batch of a single part sustainably? And can the data that we access help us achieve that? And think about such systems and autonomy. Of course, robotics systems come to mind. And we can apply the same kind of system thinking in manufacturing systems. So basically, the information that comes in such system via their sensors goes into a perception module where it is processed, and then certain map and planning is performed in this planning and decision module, and finally that goes into the control module and gives commands to the actuators in the manufacturing system. So this is similar to robotic systems. In manufacturing, we need something extra. Because we cannot measure all that we want to measure, we cannot look at where the tool is drilling exactly at the surface where it is drilling. That's difficult to sense. So we need to be able somehow to model that and predict that. That's why I put there indirect sensing. And we also need some additional process knowledge. So what is happening exactly inside the part which is being drilled. And that comes from either simulation or some domain knowledge. And keep staying here with the robotics, we can very much make a parallel with the levels of autonomy for autonomous vehicles, where the low level basically is a manual driving, and you need to look at the road and you need to turn the wheel, whereas where you go up in automation, you start being more and more hands-off until reaching the high levels, where the car goes by itself, like the Waymo taxi, and finally it can go anywhere, so not just in limited environments, but in very large, well, everywhere possible. That's the dream. And if you think about manufacturing systems, where in autonomous vehicles we are at level 4, for example, for manufacturing systems we are still between level 2 and 3. So very few such systems actually are able to self-adjust and being operated autonomously. they always require an operator. Even very few of such systems have closed-loop control at all. So they just get their parameters tuned before operation, and that stays. And that then is new set of parameters needs to be found for each subsequent part that needs to be processed. So they cannot really operate with large number of scenarios, large number of parts, and they cannot operate in changing conditions, which is the opposite of autonomy. So when we talk about data in such systems, there are several specific characteristics of the data which can help achieving this adaptation. So the measurements from such systems in general, the operation, so there is a large variability. That is in the quality of the parts, in different components that can be replaced and not making one machine different from another, which is supposed to do the same thing. Then the operation of such system is repetitive, and that is on different scales. For example, they might produce many parts in a batch with the same operation, but also even in building one part, it's the same, let's say, the position of layer over layer over layer. Then we have process drifts, we have noise in such systems, and very importantly, process and safety constraints, and lack of in-situ measurements, as I also mentioned before. So knowing about this, we can efficiently pass data in our optimization algorithms, which would provide us with experimental inputs. And I will show you particular ways to do that. And this data that we gather can also help us further, so we can build digital twins of such systems. The digital twin is a virtual replica of one instance in the manufacturing plant, let's say, so one machine. It captures one single machine. And now I will start with a method which is very data efficient, so it needs a little bit of data such that the machine can readjust its parameters. And later you'll hear more about digital twins and other methods. So this method that I'm talking about is also known as Bayesian optimization. And the goal is to optimize some performance metric. So we want to find good parameters for that metric. That could be good controller gains, that could be good process parameters of a manufacturing process. So for example, feed rate or speed of some spindle in a machine, and so on. In this case, I will demonstrate it with, for example, tuning gains of a motion system. And so we have this performance metric, let's say the position error, and we want to find good controller gains for that, but we don't know where they are. And we need to do that very quickly, because if you think in manufacturing terms, you don't want to produce 100 parts to find good parameters. So we do very few measurements. We do just these two measurements. And now we can use probabilistic models to model the dependence of our gains on the performance metric. And now we can predict for the whole range what is the performance. And we can predict that with very small uncertainty around the measurement points and with high uncertainty where we don't have measurements. And if we have now some auxiliary way to say where to measure next, such that either we find a better optimum than the one that we have so far, or that we learn a lot about the whole behavior of the function, that would help us. And we have that. So this is called acquisition function. And it just balances this predicted mean and the uncertainty value around for all the range. And it tells us where it's the best to measure next. And in our case, it tells us, okay, measure somewhere where we don't have a large uncertainty, where you can see the dashed line. So we measure there, we update our model. And now we know a lot more. We still don't know about half of the range what to do, but then our acquisition function tells us, okay, measure at the end to figure out what's happening. We measure there, and then after very few measurements, we are at the optimum. And this turns out to be efficient for manufacturing processes, because the goal is not to model very well the process, the goal is just very efficiently to find the optimum. And on top of that, this could be combined with safety constraints. So with every iteration where we need to update, we don't violate the safety constraints of the machine. So we did that for all these systems here that you can see for additive manufacturing and for CNC machines and for plasma spray coating. And I will show you a particular example about a motion stage. This is this motion stage here with the blue frame that is very precise and used in semiconductor manufacturing inspection. It's this system, and this was video is supposed to work, but it doesn't. So basically, we define here, again, at every move of the stage, we want to find the best possible performance, and we don't want to have vibrations, to excite vibrations there. What we tune are the gains of the controller, which is in this machine. And we cannot change the controller itself. We are limited. The controller is fixed. So we can only change the gains, and we apply this method. We have a safety constraint here. This is the velocity error, the Fourier transform of the velocity error, which with every possible measurement that we do, we monitor that this is below a certain threshold so that we don't see vibrations and we don't get the instability in the system. Because we want to continuously operate this optimization while the system is in production. And to do that, we have to also be able to predict for the next moves what should be the good parameters. And we do that as a separate function of the length of the move. So we need some kind of parallelization and synchronization to do that. And we do updates between the runs. So every time after the system moves, we update for a whole horizon of different possible moves and take into account the stability considerations. And that turned out to work pretty well. So we were able to show that we can adapt to different payloads, so we can put different instruments on top of that system, and also different lengths of the move. We compared it with various different controllers and tuning methods, and it worked better than those. So we were happy for that, and that was a real industry collaboration with the producer of such stages in Switzerland.
It's about the optimization approach that you mentioned before. Yeah, it's indeed it's a good approach, but maybe the main drawback is for the number of iterations that is needed to find a solution, even if it's not optimal, but it can be acceptable. Sometimes with companies, it's really difficult that they give you an access to their process, and
yes. Yeah. It's true. So in that case, first we had the machine. They gave us the machine to work with. And it's true that it takes some iterations to reach an optimum. But in this case, I didn't talk about the details, but you can see here, we have a pre-approved, so to say, limit, an upper bound, or actually a lower bound possible of the performance. So if the performance is better than this, it's acceptable, basically. So we could have some moves which are not extremely good, but are still acceptable, and then after some time we would find the optimum very fast. You can see that here, for example. So we have a cost which is increasing, but then very fast we have adaptation, and it goes to a near optimum, and then again when some change in the payload happens, it goes down after 1 or 2 moves, basically. Yeah.
Another question is more about when you change the process, or you keep the process, but you change the projects, for example, and you need to retune the process from the beginning. I think it can be interesting also, because I'm working on this topic also, that we can learn from the first tuning to already speed up, for example, especially using BO, to speed up the optimization for a new project. So, that can be a good extension.
Yeah, we might talk after. Thank you.
Thanks, everyone. So I'll talk a little bit about some of the other applications we have, starting like following the thread on the precision motion stages. We talked about digital twins, and I'm going to show one example of some other related applications we did on the precision motion stage application domain. I just wanted to define a little bit what we mean by digital twins, because there's actually a lot of different motivations and definitions that are floating around, but I feel like it's starting to slowly converge to something that twins, it's a purpose-driven software replica of a physical or digital asset. So it doesn't actually have to be necessarily a digital asset, physical asset. We could think of digital twins of controllers. And the idea is to combine modeling information, computation, data analytics, and some form of communication interfaces. So I think one of the key things is that it needs to be sort of reflect the specific instance that we're dealing with rather than a generic model. And this bidirectional, either for monitoring or controlling data flow, I think is some of the key aspects. So one idea we had is, okay, actually it's a really nice follow-up to the question we had about multiple runs and accessibility to the machine. So then we asked the question, what if we cannot run, or we do not want to run additional steps on the machine to tune the machine? Well, a simple idea would be that I have a model of that machine, so I'll just run some trajectory optimization and put it on the machine. This is really following that ideology to say that now we have this is a similar but different precision motion stage we have in Zurich. And we actually had a very detailed, high-fidelity neural net model of this precision motion stage. It's accurate up to the repeatability of our sensors. It's a data-hungry model, but we can tune it autonomously, letting the machine run for a few minutes, collecting data, and then we train a neural net. Now, the question was, can we integrate this into a digital twin such that we can do trajectory optimization using this complex model, and then we do everything virtually, and then we just take the inputs and run it on the real system. And there are certain details that I'm just not going into here, but the idea was to use some form of learning-based model predictive contour control ideas, and the learning here is between a nominal linear model and the digital twin model. So when we do this, here are some experimental results. So this idea is that on the corners of the figures, you see the two different geometries that we want to follow. So we start here and follow an octagon or a circle. The idea is to use the digital twins to tune everything offline. So we do some level of tuning, but everything is offline. So we do not run anything on the machine, and the machine has not seen these trajectories. So that's the key idea. And when we did this, the quote-unquote sim to real gap of what we optimized versus what we ran on the machine in terms of the RMS error was actually quite good, 3 to 5 microns, but the maximum error gap was much higher, which is just indicating that there are certain aspects of the liveness of the system that cannot be predicted by the digital twins. But in the end, we were able to improve the performance at about 50% with the increased overhead due to our computation. Okay, so Another idea that we play around with quite a bit was to use iterative learning control. And again, in the interest of time, I will be very brief about this, but the idea is that we run one trajectory, we learn from that trajectory, and we update our input in the next trajectory, which is actually quite perfect if you have a repetitive manufacturing process. Now, we have developed some methods to deal with convergence guarantees under model mismatch, under constraints, and under noise. And then the idea was that, we prototype this in precision motion stages. We asked the question, could we go to some of the other processes we showed in the earlier slides? And in this case, we wanted to test out this, repetitive control, iterative control ideas on 3D printing applications. So specifically, the application we chose was metal printing, where we actually have metal powder that we lay on each layer. And then using laser, we melt the metal powder and let it cool down to obtain a three-dimensional geometry layer by layer. The reason we wanted to do this, and this is one point I wanted to highlight, is actually not that we had the controller and we looked for an application, but we were approached by our colleagues that are doing this application saying that there's quite a bit of process variation and reliability issues due to things like terminal management and warping on the system. So we thought we could use these ideas to build this layer-to-layer control loops. And so what we ended up doing on our experimental setup was to build this layer-to-layer control loop where we actually use thermal cameras to look at the temperature field between the layers, and then use our ILC-inspired, let's say, controllers to print two parts side by side. And then what we see here is that the thermal accumulation, so on the plot right here, you have the blue one that is the reference print, which is the quote-unquote state-of-the-art, which is just to apply constant power. This is an inverted pyramid geometry that undergoes quite severe heat accumulation, as you see here. So this is the surface temperature over the layers. And you see that our controller puts the maximum power at the beginning to track the reference as best as possible, and then gently tunes down the power to track it as long as possible. So at the end, we also saw these fluctuations, which were caused by some additional physical phenomena that we didn't know at the time, which actually ended up even further research, and that's ongoing work. But even on the physical parts, you see right here, so these are the cuts of the corners of the part, you see qualitatively that the definition of the geometry is actually much better with the closed-loop control. And I think I'll stop here in the interest of time. There are a few more slides, but I maybe jump over to the... we also did this for in-layer control, so that was the rest of it. But yeah, I think this will come back again on the panel talk. But really, just to reiterate that manufacturing and robotics are data-rich application areas, and there's actually quite a bit of high-impact research opportunities by leveraging control optimization. And we have a lot of these really nice examples where the practice inspires theory. And this is thanks to our colleagues. Like, there's actually a very large team that was behind this work and our funding. And yeah, I can.
Without big introduction, I'm with ABB Motion, and I have just one slide quickly showing what that actually means. I mean, it's called industrial drives also, electric motors, basically moving things in industry. My presentation will have no equations inside, and it has also no curves, because I thought I would rather talk a little bit about cases where we managed or failed in moving a control approach into a product and into money, basically, in the end of the day. So where do we stand? Where could we go? So when we talk about a drive, it's actually a drive system, and these things can be fairly large. They can stand next to each other, be connected to the same process. They can even be maybe very hard connected with each other. And so you stand actually in front of a system that has many similarities with the energy system, but it's moving mechanical energy or some process chemical energy in a plant, but still it's a coupled thing. So such a variable speed drive, yes, it is actually, well, it should be called a variable torque drive. It is actually a torque source, but last but not least, it's a control device normally. And that's what is expected by the user that it should do. It should ideally read the mind of the user and do the perfect thing that he just had in mind. Applications are really everywhere in industry. But also like moving ships or in transmission, moving power, compensating reactive power. So there is numerous applications for more or less the same hardware building blocks. If we take a control perspective on it, what it actually is today, then we try to structure it in layers. We try divide and conquer approach. So we have somewhere some power electronic systems that we have to control, and that has typically to happen on very fast timelines, 1 kilohertz, 10 kilohertz in this range. That's what many people refer to as a topology controller, and people are doing research in this corner, still do. Then we have somewhere a middle range application control. So as an example, that could be controlling a motor speed, but relatively abstract, not knowing what the speed actually means. Yeah, the speed is responsible for discharge pressure of a compressor or for mole flow in a compressor. That is then actually the third level where we can talk about the system, drive system control. And that's actually the most interesting one, because this is the one where the customer is sitting, the one who invests in a drive system where he has some demands and some expectations how his system should operate. I on purpose put below as examples, I put the industrial process side view. So the topology, this is controlling currents, maybe controlling power flow. Then in the middle range, we have typically torques and speeds. And then as an example, discharge pressure of a compressor. But we should never forget there is also the other side. We're also connected to the electrical grid. And I've been in a few sessions now over the conference, the big topic on how to handle energy flows in the grid and help stabilizing the grid. So the line transformer current is again the low-level thing that we would actually control, but that's not even half of the job we should be doing. We should control power, reactive power, active power, but then we should also do more things. We should do good things to the grid, like helping controlling the voltage in the grid, or helping dealing with transients in the grid and mitigate them. But traditionally, we tend to work in these silos, and that's probably one of the things that has to change in the next years, that we step out of the silos, or that we at least start to find cleverer interfaces between these areas of control. And I tried to put that a little bit on a timeline, and I think we are not even moving with the same speeds on this timeline. On the motor side, when it comes to controlling power going into a process, we are actually moving slower, is my impression, than we are moving on the grid side when it comes to do ancillary services on the grid. So, I mean, traditionally, yeah, we have been controlling the speed of machinery, or on the grid side, maybe helped a little bit in providing frequency regulation, inertia support to the grid, things like that have been done already now since 2-3 decades. And then on the grid side, I think interoperability has become an issue, or has become a topic that was not only researched, that has also found now results in norms that came up, especially when you talk about railway industry. I mean, what is interoperability in this sense is how does an active unit have to behave in the grid so that things are really working together. I mean, there is one controller, potentially a pretty aggressive controller, that just has some bigger target in mind and will just pull power from the grid, whatever it takes, yeah, jumps or oscillations and so, and may actually disturb another converter, which is maybe a little bit softer, and then doesn't get the power because the other one is unfriendly and takes all the power and is hampering the voltage of the grid by its behavior. In railway, this has been seen since the late 90s, and there are now norms telling how converters have to be there, but these are typically very conservative criteria that have to be fulfilled. I mean, total passivity of the converters throughout the whole frequency range, and I mean, yes, that will work, but maybe conservative is not always the best. The complexity the grid gets and the complexity the applications get. On the grid side, interoperability has now already done the next step. Some countries have made big steps forward, like the UK, where they clearly identified a long list of ancillary services that an active unit in a grid could fulfill. And that needs not to be a windmill or an SVC, a static converter that is doing reactive power compensation. This could also be a very large industrial driving some pumps, can actually alongside also provide some of these services. And this is now slowly coming, and people are now thinking, how do we make ends meet? If I have a control target to pump water in a municipal waterwork, how much freedom do I actually have to make compromises? And so many papers presented here in the conference on charging vehicles, but there is numerous very similar applications which are actually more common even. I mean, they already exist, whereas the electric cars are just coming up. And then the next thing is, I think, is really behavioral rules that we expect to come up, so that we are not just putting some equipment somewhere, we are putting an agent somewhere into an industrial process, and this agent gets some rules he has to fulfill. He has basic rules he has to fulfill, power flow, but he has also etiquette. Yeah, so some things he's allowed to do and some things he should never do, and like this behave without us doing a top-down design of a classic control system. And I think what will come then as a last thing, we talk a lot about using data. I think you mentioned also using data for analytics is now becoming more and more common. That all these relatively clever devices that have a lot of computational power, they can collect a lot of info on the health of the driven equipment, but they could actually start to share that information also for the benefit of controlling things more optimal. So I chose 2 case notes, one that was really successful, a successful transfer, but I want to really use the opportunity here to tell a little bit the story, because it came now sitting here in some of the presentations, it occurred to me that probably we have an issue of time synchronization. So it's not just that industry is not just slow, but we have to be in sync. So if you develop products that you sell for 10, 20 years, which is quite common for the products that we have, you have to be there with a new technology in the right time. So that's the one thing. And then you have to qualify it, and you have a chain of customers. You sell, or we, for example, sell to a compressor manufacturer. The compressor manufacturer sells the system to a pipeline operator, and then that guy actually probably even has some other involved parties really running the show. So you have to convince everyone. So the timelines are different, and then this morning I also thought maybe we're also violating just the sampling theorem, that the hypes, the highs and lows that we see on technologies in academia, sometimes they're just oscillating quicker than we are able to sample. So my master thesis was a self-learning controller using 3 neural networks. It was done at ETH in Zurich, but together with ABB. And this was 1994. And I see papers now again, and we flopped completely. I mean, it worked, but from a money perspective, this was basically a flop, because it had numerous issues that we figured out we will never be able to resolve if we start to use something like this. And I see now, of course, 20 years, 30 years later, that we are moving in big steps further, but this is maybe the hype was already over 1997 when there was this economic crisis in Asia and things just, yeah. But a good example on how we managed to take something new. I mean, our world is really, like Sylvia said in the introduction, PI controllers all over. You try to isolate things and tune a little bit, and that's it. That's how many industrial processes are run. And in around 2002, of course, people were really talking a lot about model predictive control. We were sitting together and said, what is in there for us? And the most obvious thing why we started to look into it, they said, yeah, power electronics is a very typical thing. You are switching the power semiconductors, and then the system evolves over some time, and then you're switching again, and it evolves, you're switching again. That sounds like it could be MPC could be used to control such a power electronic converter in a far more optimal way than classical controllers would do, averaging controllers would do. And then we also discussed a little bit what is very typical, these 3 levels. If we look in practice, and this is still true today, what we are suffering from is typically that people don't do anti-wind up correctly. I mean, it's also practically sometimes impossible to get this sorted out. So we have many problems. You could just put under the headline of balance of plant is not okay anymore. So somewhere something saturates, then the next controller doesn't know how to deal it, and boom, in the end the whole process just stops, and 1 day of production is lost. And we felt, well, actually MPC would also in this case be a good approach, because normally we are dealing with constraints coming in, and especially if 2 or 3 come in with just PI controllers, if that was not thought of before, you're going to fail. And so 25 years later, we have model predictive controllers running in actually one of our, from a technology perspective, oldest drives. So these are drive systems that we have been selling since the early 80s. from hardware perspective, but we put completely new control system into it now using a model predictive approach to do the topology control in this case. So these are converters where they are connected to a grid. The converter itself has a storage inside, a big inductor where you can basically store energy as a DC current in the inductor, and then on the other side you have a synchronous machine where you again you rectify or you chop this current into an AC so that you can turn this synchronous machine at the speed that it needs. And throwing MPC at this problem, it exactly brought us these the advantages that we were hoping for. These systems, they are interconnected. The case note that we had, and this is it's literally now the 25 years that we have seen going by, is an announcement, the press announcement that we just did in May this year. The plant has been up and running with such a model predictive approach since 4 years roughly now. This is in Norway, a gas export station with 6 drives, driving 6 compressors, 41 megawatt each, and this is accounting for about a sixth of Norway's gas exports. It's going to in a pipeline towards the UK. And what it brings for the customer is that this converter is really able to deal with whatever unforeseen situation in the grid that you could think of. The Norwegian grid is quite crazy because the power lines run north-south, the winds blow from west to east, and so you get a lot of disturbances because phases are touching the zero lines and they have ice on them, so they are hanging down with the ice, and you get single phase dips, double phase dips, and you get like 40 such events in a stormy day. And in the past, this has brought down the export station several times a year, so especially over the winter period. And Equinor allowed us now to, so the Norwegian gas company allowed us now to also publish that we have been saving about, since it's in operation, about 160 such events where the whole export station would have come down. The current controller is now just struggling through every situation, but MPC is not giving up because it knows exactly what options there are still, how to fire a thyristor and still do some current and still drive the compressor. Another example is one from also from the oil and gas industry actually. When you liquefy natural gas, it's basically just a huge fridge. So there are compressors that are cooling down a refrigerant, and with this refrigerant, you're liquefying the gas in 2-3 steps. And we have been approached by the end user, so the company that runs this facility. This facility has several such lines where they are cooling down the gas, and this is on a massive scale. And so you have a fairly complicated. No, actually, the process is actually fairly simple. You just want to cool down the gas. You can play a little bit between the different lines that you have. So schedule a little bit which line is producing how much. If you have one line going down for whatever reason, you basically have to burn the excess gas. Because you cannot stop the gas coming from the well. So it's pretty dramatic. So they have a very big interest in having very high availability of the plant. And also when we went into this system, having some hardware failing is actually extremely rare. I mean, this is like every 5 years maybe you can have something in the hardware failing. But when going through all the reasons why the plant had actually tripped, we see that it's again this balance of plant thing. So one controller is trying something, is hitting on a limitation, cannot really interact with the other controller, and in the end just brings down the whole plant because the 3 control levels get confused. And so we started to look into it and said, hey, let's come up with something. We called it a soft trip. So this is something a bit more than an alarm. So it's not an alarm. When you get an alarm from a system, the operation goes on. But in this middle thing, we say the operation is actually deteriorating in a predefined way. For example, a torque limit kicks in. Motor runs hot, torque limit kicks in, but continues to run with a torque limit. And a signal is sent to the next layer of automation, and the next layer can decide what to do with it. And then, of course, you still have a number of trips, but there it's actually surprising. It's about 10% of the things that could potentially shut down the system. You have no option. You have to shut down the system. But 90% you can turn into something more soft if you think a little bit about strategies. But then the thing is, how do you now make that so that these processes work together? And this is actually the thing where I wanted to bring it as a bit as a negative example. The thing that we really managed is that we just have started now a countdown. So we are limiting the torque and we're counting down, and depending on what is happening, you get a minute or you get 5 minutes to react. And this has also been implemented, so you can imagine as we speak now something would happen, some operators will see some red lights and horns and they are running around and they try to reshuffle production in order to save the processes as a whole. But of course we said, well, at least the minimum we should be doing is we are not just giving a countdown, but we are also showing a prediction. So we say, well, I'm running now at reduced torque. If you allow me to run at even further reduced torque, then I can operate forever. So I give the next layer some option to decide. And then the last thing that we were thinking, well, actually the next layer should also be an MPC as we are, and we should parameterize somehow our behavior and tell him with a handful of parameters to be defined our health status. And an optimizer on the next level can really optimize. Didn't work out. We can discuss in the panel discussion why something like this is not working out. In brief, there are too many players. So if we talk a little bit of, to conclude the research outlook or the roadmap, I think we have to become kind of object-oriented with how we do control of all these subsystems. Not brute force, top-down or bottom-up, however you want to call it, so someone making, but really objects that follow rules, that have interfaces, can talk with each other, and then design them like this. Reality is we have many hardwired things. We just get a 4 to 20 milliamps signal telling us how quick we have to run or how much torque we have to make. Such things can also be found in the book chapter, of course. We have detailed a little bit more what we think in which directions we should be going. It's always both sides, motor side and grid side. But I think we have to shift paradigms a little bit here. So with this, I'll conclude my part and...
Speaker is Tariq Samad. And then after Tariq talk, you will have the opportunity to ask questions within the panel session.
Thank you for the invitation, Sylvia. Great to be here. I'm Tariq Samad. I'm at the University of Minnesota at this organization called the Technological Leadership Institute. But I spent most of my career, 30 years, with Honeywell in various applications and doing technology development and research in various applications of automation and control. But my job here is to tell you about the introduction, tell you about this new document report called Control for Societal Scale Challenges, Roadmap 2030. How many of you have looked at that or have seen that as yet? Yes, one person who I know, and 2, 3, 4. So most of you have not, yes, but which is good. So this is a document, a pretty significant piece of work. It's been produced by, I think I should have had the, hang on, I'm just seeing. No, I thought I had the editors-in-chief, but they are the editors of this report. You can't read them actually from this. But the people driving this effort were Anuradha Anaswamy, Kalle Johansson, who's one of the co-chairs of this conference, and George Papas. So I was a lead co-author of a couple of the chapters of this report, but I'm talking about the whole thing here. You can access it at the web. I will point out in particular that there are videos available for every chapter and for the overall introduction, and they're very professionally developed videos, and I think it would be better for you to get an overview of the report by watching the video than by hearing me talk. So I'm going to switch to the video. It is by Steve Brunton, which some of you may know about, and I have lots of things here. Okay.
This is a publication of the IEEE Control Systems Society, and it's just a really fantastic document that outlines what are the major societal challenges that we humans face today and in the future, and how is control theory well posed to be central in solving and addressing these challenges. So I'm really excited to introduce this to you. I'm going to put a link to this document in the description below, so please click it, download it, and read this for yourself. I'm going to give you the high-level overview of what you're going to find in this document in this video. So this was a collaboration between a pretty large number of some of the world's leading foremost experts in control theory, edited by and organized by professors Anaswamy, Johansson, Pappas. And so, I recommend, pausing this or downloading this and checking this out. It's really a star-studded group. Some of my heroes in control theory are among this author list, people I respect and work with. And it really highlights that there is a coalition, kind of this group of diverse opinions coming together to really outline and address what are these societal scale challenges and how can control theory help. Okay, so really excited to walk you through this. This video is going to be the introduction, where I'm essentially just going to tell you what the various chapters are, how this is organized, and give you a little teaser for what you're going to see in the subsequent videos. Okay, so this document, it's almost a book. It's about 250 pages long, and it's a pretty hefty read, but it's also tractable. So there's been a lot of polishing and streamlining of these ideas so that it is focused but very comprehensive. So this video covers kind of the introduction. This is, chapter 1 of this roadmap is an introduction. This video gives you just a high-level overview of what the topics are. And I'm going to have short, focused videos kind of demoing what you're going to see in at least a number of these chapters, if not all of them. So chapter 2, this is really kind of the core motivational foundational piece of this roadmap, looking into what are the societal drivers that are driving the future, the future efforts in this field. So things like climate change, something that we need to address, that control theory is going to be central. We're going to need to measure, we're going to need to model, we're going to need to predict, estimate, and control the system to deal with climate change. So that's an example of a societal driver. Things like biotechnology and biomedical technology. How do we deal with pandemics and diseases? Very topical now. Those are the kinds of societal drivers that we're going to talk about here. And this is a pretty hefty chapter. I want to say this is almost a third of the entire roadmap, a little bit less than a third of the roadmap. But really, this is the set of common issues that we humans face that we think control theory is well poised to be central in addressing. Okay, very, very important, very interesting read. I highly recommend it. Chapter 3, Technological Trends, talks about what are the trends in technology more generally than control theory at large that are driving some of our advanced capabilities that we think, in the next 10 years or so are going to really be affecting how we develop control theory solutions to address these societal challenges. So technological trends could be things like the rise of big data and artificial intelligence. This is not specific to control theory. This is a societal trend, a technological trend in general, but it's going to change how we do control theory and how we do modeling and things like that. Things like the electrification of everything. So increasingly every aspect of our industrial energy, power grid, everything is becoming more electrified. That is a huge technological trend. The Internet of Things, autonomy, robotic systems, these are general trends in technology that, again, are going to drive our advanced control capabilities and how we're going to be thinking about solving these societal level challenges. The fourth chapter, this is one that's kind of near and dear to my heart, is emerging methodologies. And this is really kind of emerging methodologies in control theory that are developing these advanced capabilities. Things like the interface of machine learning and control, autonomy, cyber physical systems, robotics. So this is really focused on what are the emerging methodologies that we as control theorists have access to, kind of driven by these broader technological trends that that we can use to start solving these societal level challenges. So I hope you can see that there is, some thought process behind this abstraction and the modularization of these chapters. They really do build on each other. So chapter 2 is highly motivational. Chapter 3 is, what's happening in society at large with technology. Chapter 4 is more focusing on kind of how this is applying in control theory capabilities. Chapter 5, I think, is really, really important and interesting too, which is technology validation and translation. So how do we actually take these control technologies, these kind of emerging methodologies, and how do we start to scale them into being able to solve these societal level challenges? This advocates for the need for benchmark problems, for validation problems and validation data sets. We're going to need our control theory solutions to be trustworthy, explainable, verifiable, especially when we're using machine learning techniques, in these kind of hybrid machine learning control systems. And so this really talks about what are some of those challenges to actually scale this up and verify and validate and actually get these into, industrial scale solutions. Chapter 6, again, one that's very, very close to my heart, is education. So I contributed to this chapter a little bit. And the idea here is, if we want to have these solutions to these societal level problems, we need a workforce of engineers who have the training to actually use these methodologies to solve these problems. So we want our engineers to have these basic capabilities in control theory, in machine learning, in validation and translation. So kind of everything in this roadmap, we need to be beefing up our educational efforts so that we're training the next generation of engineers that can actually, enact and develop these technologies for global good, for societal scale change. Okay, so very exciting, something, again, I'm very passionate about. And again, I want to just point out, I'm going to have, hopefully, videos on, at least most of these chapters, if not all of these chapters, to give you kind of a little sneak preview of what you're going to find, but you're going to need to actually download and read this document to get the full depth. I'm going to give just very topical, kind of high-level anecdotes from these chapters, but there's a lot of substance there that I'm not going to be able to cover in this short time. The last kind of big chapter is chapter 7, ethics, fairness, and regulatory issues, which addresses things like, what are the actual issues with deploying societal scale control solutions to solve these challenges. One of the things I really like, and I've seen in lots of the chapters in this roadmap, is this focus on fairness and equity in how we actually deploy these control solutions. So if you think about the equitable distribution of medical resources and medical care, that's actually a control theory problem. That's a constrained optimization problem. And so I just really like this kind of modern perspective that we need to be thinking about fairness and ethics and equity when we are dealing with these large-scale control theory solutions, so that we don't only help a few and not everybody. Okay, so really kind of a neat perspective here, and an important one too. And then finally, chapter 8 is kind of a conclusion, summary, recommendations. How do you take this all together? What are next steps? How do we get started? How do you, kind of join the cause? So really excited to walk you through this. Again, this is a collaboration with a number of amazing researchers that I respect very, very much. And so I hope you get as much value and kind of education out of this, and inspiration too, out of this as I did. All right, thank you.
I hope that will motivate some of you to download and read the report or parts of it. What I want to do in the rest of this talk is to give you an overview of some of the content that's more relevant to the theme of this session. So again, I'm showing you just the overall sort of table of contents, just so you can take a glance at it if you can read that at all. But then the two parts I'm going to focus a little bit on is, one is climate change mitigation and adaptation, because I was a co-author on that. And in fact, it's kind of organized around industry sectors and application sectors. And the other one is technology validation and translation. So regarding this chapter on control for climate change, in fact, there's been in the recent issue of Control Systems magazine, there is an article came out that's an extended version of that chapter, and so you can access that now, and it really addresses climate change, talks about it in a broad sense of what are the challenges, but also specifically in terms of what are the targets of opportunity for control scientists and engineers. And these targets of opportunities are organized, as I was referring to, by industry areas and application domains. So we have electric energy systems, power generation, transportation, homes, buildings and facilities, industry and manufacturing, and you can see the list. In each case, we've got a discussion of a few paragraphs, and then also, just as examples, we've identified three application opportunities. And so I'll give you an example of one of these domains, which is industry and manufacturing, right? So what we talk about here is, first of all, about 34% of global greenhouse gas emissions are from the use of power and heating in industry, right? And it's important to recognize, by the way, that's not just electricity, it's also heat. Heating is really important in industrial plants. In fact, because heating is important in some plants, it makes them hard to electrify. So cement is an example of that. It's not so easy to think about how we would use electrification to replace the energy consumption in cement and some other facilities like that. There's a lot of drive towards circular economies by more efficient use of resources, reducing the waste that's produced in these ones, and having more sort of reuse, and that leads to inherent feedback loops as well. And certainly there are technology enablers now as well with Industry 4.0 and smart manufacturing. The example opportunities we highlight here, and these opportunities are categorized by short-term, medium-term, and long-term. And we say short-term means we have the potential to have impact at societal scale by 2030. And medium-term is by 2040, and then long-term is post-2040, right? So the example opportunities: advanced process control, optimization, and data analytics over the manufacturing value chain for increased efficiency, utilization of waste heat, and equipment transitions towards greener fuels. Again, referring back to that fact that we can't just expect electricity to do all the job for us, we'll need fuels as well. 2, control co-design for greenfield net zero projects leveraging Industry 4.0 enablers, right? So, of course, they are what are called brownfield facilities, which are facilities that already exist, and we need to reduce their carbon emissions. But a huge opportunity is new projects, greenfield projects. Well, now we have the opportunity, a fresh sheet of paper that will provide us more opportunities to apply some of our techniques and reduce emissions. And lastly, focusing more on storage of greenhouse gases such as methane and CO2 and their long-term utilization. That's also a really important need. We'll need to do that as well. So that was one example of that. The other part of the report that talks about industry and innovation and really talks a lot about how do we get from research to practice. And so many of you have seen technology readiness levels. So here's a chart of those TRL 1 through 9 and TRL 1 through 4, as it's sort of identified here, as kind of lab-like activities. Then you may do things in simulation, and then you may get to the real world. And a figure from this report shows sort of the validation steps and tools that are involved for each step. So you have to think about, many of you in the work that you do as researchers may be thinking already beyond the basic research and the foundational research. And the next step is really prototyping. But even in the prototyping and validation stage, there are these steps you want to go through. You want to think about evaluating the application, analyzing its performance, then developing a prototype and evaluating it. And then next step is actually demonstrating the prototype, and that ideally would be a real-life experiment. So that aspect is discussed in this report too. It also identifies the economic aspects of some of these domains that we often don't think about in the research context, but that are so important when we think about, okay, how is this going to go to market? Is this going to go to market or not? Will some company be interested in taking this research that we have done and making products and offerings out of it? This chart is actually from another article that I would also think was an interesting read for anybody interested in how control research needs to engage with industry. It was appeared in annual reviews in control a few years ago now. But you'll see it refers to sales volume in billions of dollars per year, global sales volume, and growth rates, right? And the other stuff is the period for CAGR. CAGR is compound annual growth rate, but it's basically the average growth rate over the horizon considered, which is the period for the CAGR. So things to note here are sales volumes, right? And they're all so substantial. We're talking about, this lowest number here is $10 billion a year. That's aircraft flight control. Something like industrial control is $117 billion. Smart home automation, which I've highlighted, is $75 billion, or was $75 billion in 2018, but at a growth rate of about 12%. So these are the numbers that in industry, people look at a lot to see, okay, where should we be investing in? Where is the money now? Where is the money going to be, right? And then there's also investment in cross-industry technology areas that's also shown here. Let me see. Okay, yeah. I think I will just stop here. This is actually a really interesting chart, and maybe I'll get to refer to it in some of the Q&A. And again, I'll remind you about this roadmap report. Those are the editors listed there. Please do look at it. There's a lot of insight there for anybody who's interested. Of course, we're talking here from the point of view of innovation and industry, but actually there's enormous insight for anybody interested in control. So thank you very much there, Sylvia. I think we can move on to the next part.
So I would like to invite actually the other speaker. Now we will start a panel discussion. And let's see if everybody has audio. I guess we do, yes. So, Alisa, perfect. Actually, first I would like to give you the opportunity to ask questions to the speaker about their specific talk, or about the general topic of technology transfer between the respective fields. We had, yeah, there is somebody with a microphone. Well, yeah, thanks.
Yeah, maybe one question is about the TRL level. I think that's the most maybe important part now for research. Yeah, if you deliver something that it cannot be used by companies, so yeah, it will be difficult to convince them. And I think it's very important to reach certain level, not maybe at the two highest level, but at least 6 or 7, that the company can directly use what is developed. Otherwise, they still need to make it robust and feasible.
So sorry, I missed the question though.
It's more a remark about the TRL level.
Okay.
Yeah.
Okay. Thanks.
Thank you for presentations.
I would say TRL 7 is where we would, for example, move something from corporate research level to the business areas. TRL 7. Yeah.
And I would say that many companies, behind you there's a question there too, but I'll meanwhile just add how TRLs are used varies a lot. Across industry sectors, across companies. What levels are used? I know one company that has 5 TRL levels. They don't really call them TRL levels. I know others that use 9 levels, which is similar to what this TRL scale that was started with NASA. It depends on the industry sectors a lot. It depends on aspects like how important is it to really produce a product that's a perfect fit. If something's going to be out in the field for 15, 20 years, you need to have very high assurance. On the other hand, if you're developing let's say a a new game for your smartphone, that level of steps is not usually followed, and people just throw it out and expect that with feedback things will get improved.
How much do you think this is actually related, is a question for everybody, to the specific technology and the use of the technology, right? If it's technology that is used, for example, only by like large industry, so like complex scenario, or also if it's really driven by, let's say, financial shorter cycle, like consumer products. Let's say consumer product versus industrial solution. This is...
Yeah, I mean, just a quick point is like TRL also translates to, you know, some people call it innovation readiness or whatever. So like, even when you start trying to build some scientific foundation and you write proposals and everything, people consider different aspects. Like you were saying, like it's not, you know, if I'm trying to start a research direction that hopefully will end up in industry, people are interested in how solid of an idea that is versus if I'm pitching a product, they're interested in how reliable that is. So I think different communities have different, let's say, focuses. And I'm more familiar, less familiar with the product side, obviously, but yeah.
I think, you know, so there are many factors that you have to think about. So some industries, for example, are very highly regulated. You know, the aerospace is one, medical devices is one, right? Other industries are less highly regulated. Even like building automation is not so highly regulated. And certainly developing a game on a smartphone is not highly regulated. So how much effort you put into the validation process and making sure that the first product that comes out is good enough for long-term use depends a lot on factors like this. And it's not just, I think it's not just large companies versus small companies, because, you know, even within a large company, there can be many different aspects like that. But it does have a lot to do with the industry sector and the nature of the technology and the potential market and who the consumers are going to be.
And just to add on to that, I think regulation is a very nice example. Just one thing I will bring up, the example I put on the slides about using control for additive manufacturing, for example. When you talk to industry, a lot of these processes are used in things like aerospace, right? Like highly regulated, very tight. Like they want to really control how you produce the parts, which then, you know, becomes a difficult question, because if you change the parameters during the process, it's very difficult to validate them. So like there's actually technological push from the research side and innovation side, but then from the regulation side, that sort of pushes back and it doesn't make it to the market because of that. So then it becomes another research question. Can we develop methodologies to verify them? So like it becomes sort of a cycle, and yeah, it doesn't become a full product until certain aspects are satisfied. But yeah, regulation is a very important one, for example.
This, as you said, probably then it gives another chance to open new research.
Exactly.
Like
and
to address this hardware.
Yeah, and I think it ping-pongs between the different levels, because it you know, moving the goalpost, if you will. Like if your idea was to just be able to control it, now additional customers say that's not enough, so it goes back and you need to develop further and validate it. So.
If I may add something,
yeah.
So
sure. Just to conclude this, and then we'll...
Yeah, just we should not forget about startups, for example. So this is one way how we could move from lower levels to higher technology readiness levels. So basically, I think we should work also on kind of outsourcing or spinning off our research in this direction.
So starter cycles, a faster cycle.
Yes.
Next questions.
Thank you very much.
Sorry, we need to...
Yeah. There's one.
It's on. Okay. Thank you very much to the panelists, and maybe one remark towards Peter. Thank you for your presentation. How long did it take? The first successful story, right? The Gasco, I think it took 8-9 years from inception to deployment.
Yeah, well, it depends if you count us. Playing with MPC was 25 years, and with the customer was 2012. We
exactly.
started.
So it started in 2012 and it was operational in 2020. But also to the broader question of automation. In my limited experience, very successful stories of deploying control methodologies in industry suffer from the following. A few months later, after we have walked away, they are switched off. Because something went wrong, and nobody knew how to switch them back on, or it was too much of a hassle, so they would rather revert to the old ones. And this has happened time and again. So what I'm missing a little bit in this picture is how do we address the readiness of the people who are practicing in industry, the readiness to accept this technology and the readiness to actually deal with it when we have walked away and the phone rings at midnight and something has stopped. Thanks.
So address the education aspect, I don't
know if it is only education, if it also relates to the resilience of the control system, to the fact that sometimes robustness is more important than performance. Yep. It is, I would say, a multi-dimensional problem that we're looking at. But at the end of the day, very often people just switch it off.
Yeah. That's, for example, where digital twins also come into the picture, that you can really, the customer can then have a digital image of what you did, and he can play around and train and play through scenarios, and he's not just pulling the cord in the end of the day. But there's many other aspects as well.
I remember once when I was at Honeywell, we had worked with some customers and developed some new solutions for them. This was in the automotive space, and they were like really excited. Things that they were taking them a month or more, 2 months to do, could now be done in 2 weeks. And it was all with MPC and automation. And then we started to discuss with them, and they were still very excited. And then they said, well, you know, how many PhDs are we going to need to do this ourselves? And we don't have any people who have that kind of background. And so that kind of fizzled out as a result of that sort of mismatch between what sometimes people think is needed in terms of the background of the people who will have to be producing the solutions, and those of us who are the controls people who are saying, hey, this is great stuff. Yeah. So yeah, good point there. I mean, we overcame it by focusing more on the tool side, and so that ended up being pretty successful, but there was this issue.
I think that also points to the necessity of, you know, trying to build things together, not in isolation, but, you know, but yeah.
How is it actually in the manufacturing and robotic industry in terms of handing it over and then having like sustainably maintain over the years a solution? Like,
I have a very similar story to this story. So I think that's usually where things are, even as startups. Like we have these solutions, or like even with larger companies, that are really nice. They're very versatile and everything. But when you hand it over, it needs to be, you know, someone needs to operate it without needing very technical background. That's something people always highlight. And also the other aspect, sometimes, you know, someone knows the process and that process has been running. So you give them a new set of tuning, let's say use BO, they just don't like the response and they like bypass it. Like, I know this is not what's supposed to happen, so I'm just going to ignore what the optimization said.
And there we would benefit from such funding schemes, perhaps, where we can bring that to a higher level, because we bring it to a prototype level or a little bit further, but then we cannot build the tools which are compatible with the company's frameworks so that this works seamlessly. This is impossible for us. So, if we are paid to do it and hire teams, maybe we could, or jointly with the companies. So I think this is where we should talk more with
and there's
political
also,
police and so.
You know, expertise to learn from this other side as well. I think that's also a key aspect, to sort of try to integrate subject matter expertise into the whatever ecosystem you're building, such that we cannot model everything. And, you know, a lot of these industrial systems run for many years and they have people maintaining them, people knowing how it's supposed to go. And I think that's usually some sort of knowledge that we, you know, don't leverage when we design in isolation, like the control algorithms or whatever. But I think there's also a lot of know-how to leverage from that end as well.
This speaks in favor of what you mentioned about joint co-development.
Tariq,
actually, I have a specific question for you on this, like, let's say, the education aspect, and then you get over the sustainable, just 1 second, about so you teach in the Technology Readiness Institute and
Technology Leadership Institute,
And one of the things exactly, also in Switzerland, there are several of these certificate of advanced study, right? So post-graduation courses, right, for specialists to deepen a certain concept. So how would this play a role, for example, in bridging this kind of gaps?
So this is a program that is kind of like an MBA, but oriented for technology types. And it really tries to match and marry people with technology backgrounds with business acumen and leadership skills. So how do you put the two together? I wonder if I can, there's a slide I missed this is like my favorite slide when we talk about innovation, okay, technology and innovation. So can I just?
Might be, I don't know if it
yeah,
was.
I'm relying on how well I know Sylvia.
And then Alpha
too.
will have the slide.
There was also another question.
Yeah, we
Yeah.
see the, yeah.
Okay. So it is called the Innovation Risk Matrix. It was developed by George Day, who's a professor at the Wharton School of Business, a consultant with over 200 companies, and it's based on his experience with so many companies. And what he maps out here is the probability of failure of an innovation project based on two factors. And it's a huge based on two factors. One is the intended market and how close it is to what you already know. And the other is the product or technology that you're developing and how close that is to what you already do. Okay? So is it same as present, adjacent to present, or new to the company? And the similar thing applies in the startup space as well, because there it's not to the company, it's to what you know yourself. And you will see that if you're in your sweet spot of being same as present, making tweaks to current products for the same customer, your probability of failure is 25 to 40%. If you go up to trying to do something that you've never done before with a new technology and you will sell it to customers you don't currently serve, you're now at 75 to 95% probability of failure. The other interesting aspect of this chart is that it's not symmetric. So innovation in technology is lower risk than innovation in the market. And I mean, based on my 30 years in the corporate world, I 100% ascribe to this chart. Mm-hmm. So this is something to keep in mind, I think, just how these factors matter in what you do. So this is the sort of thing we teach in our program, and we get into the details of that. So thank you for asking the question, Sylvia.
Thank you. We had another question on the back from Alf.
I have a follow-up question to George's question or comment earlier. It is, I totally agree. I mean, it is a fact that if you look at MPC applications, they get switched off after a while. Can we turn that as the automation suppliers, can that be turned into having a different business model? Yeah. Not selling the installation as a one-off project, but actually selling the function of model predictive control and taking responsibility over the lifetime of that.
Yeah, and this goes actually kind of vice versa all the time, and because we actually, in this Equinor case, we had already more responsibility for some of the process control things that they have. And that, of course, then helped us prototyping and working through up to TRL 7 and then 8 with them. And I think as we go into the future, you will see more and more of these models that we are running or keeping simulation models alive for a customer. So that if the next generation is coming up or the plant gets some add-on, an extra process is added, and then we can investigate. And we are responsible to keep these models alive and updated. Yeah. And that's a long trend. Maybe you see the same.
Yeah, but it comes down to economics, the benefit that these technologies are providing versus the cost associated with, first of all, of course, installing them, but B, keeping them updated so that they are not switched off, right? So in a sector like oil refining, the value of the product produced by an oil refinery is very, very large, right? I mean, they're refining hundreds of thousands of barrels of oil per day. And we did an analysis of what advanced control, what model predictive control can give you, the customer, the oil refiner, this was when I was at Honeywell, and we've published this as well. It's $1 additional profit per barrel of oil refined, right? So that's a huge economic boost there. And so if that's the value of the technology, you can afford to have a dedicated control person who can be there and adjust the models when they need to be adjusted. But if you're a food and beverage operation, let's say, right, or some other industry sector which doesn't have that value, then it becomes harder. So what we need to think about with the technology we develop is how can we lower that barrier so that more and more industry sectors, in this case you could say process industry sectors, are benefiting and can have sustained benefit, financial benefit, net financial benefit from MPC.
It's a lot the multi-benefit thing. If you manage to show that the solution has multiple benefits, this helps then. I mean, MPC in the Middle East, you will never sell it as something that helps in bad weather, strong winds. But you can improve power factor in the grid. You can improve power throughput in the system. So you have to be able to explain the advantage to the specific market.
But to explain or to prove it also, like
and to prove it.
At which level? I mean, how to prove it?
Yes.
How to prove? What would be to prove it without spending?
Well, for example, the MPC solution is software only. You can just rent it for a year. There is also the PI controller is still sitting there, and the license will just expire after a trial period of a year. So that's, for example, one approach we take with this. It's essentially, I mean, it is the same software running. It's really just the license.
So the question, how these have, I don't know if there is a follow-up question or like.
There's a different question in the front.
Yeah, okay. There was a question here in the.
Is there still?
Okay.
Okay, answered. Okay. There's a question over there.
Actually, hello. Okay. Actually, not actually a question, more or less a comment, and what was commented also from the audience moments ago that the MPC, the model predictive controllers, are switched off after a while, and that's I don't fully agree. The risk is very high, but you can keep those MPCs alive with a good service package that you Tariq just mentioned that the industries, they might not have these PhDs or whatever MPC engineers, but they can always hire from the vendor, from the MPC vendor, for quite moderate price. But nowadays, the industry wants to save money, whatever they do. Everything needs to be cheap, and they might want to squeeze down in these services. Actually, they also squeeze down in the MPC, the basic investment. Yeah. It has to be so cheap nowadays. 20 years ago, I talk now from experience, own experience. 20, 25 years ago, MPC and MPC engineers was quite high level and respected in the industry. Nowadays, MPC deliveries or APC deliveries are commodity industries. You have to sell for a very low price because the clients, they squeeze down the prices. So it's not anymore, shall we say, high technology industry. It's more commodities. Mm-hmm. I'm sorry. What I'm saying is not very constructive, but it's unfortunately fact of life.
No, I mean, it is. One point would be actually to find solution that can reduce the cost, right? So it's also another direction. I don't know if the panelists have other.
Hans, I disagree. I think companies are trying to make as much money as they can. And there are two aspects to the money. One is reducing cost. The other is increasing revenue. And so they are always trying to affect that balance. And some companies, in fact, you can actually distinguish between companies that think of themselves as the leaders, the technology leaders. They're the ones who are interested in coming out with the first of a kind product, which is a risky proposition. The other companies who want to be, say, would be fast followers. Many big companies are actually more like fast followers than industry leaders because they already have good products and they don't want to put a lot of investment into something new because if it's successful, they haven't gained the full value of what they already have out there. So they'd rather some competitor go out and do something that's better than what they have, and then they can react. Meanwhile, they take what they can. And then there are also companies whose business model is cost reduction. And they are the value leaders in a way. So you can get products at the lowest cost from these companies. They may not be the most technologically advanced. They may not be the latest, but they will be lower cost. And these companies, they will invest in innovation too. But their innovation is more about cost reduction. So that's actually another lesson as well, that cost reduction itself is a big driver for innovation. And many companies are put R&D into reducing cost in manufacturing operations, for example.
If I may add something, so in Switzerland we have this innovation agency which funds collaboration between academic partners and industry, and one of the big requirements that they have is that there is a business value demonstrated out of such collaboration, and it's not enough that it's just cost reduction. It always should have a large value creation on its own. This is the more important part, at least for that type of cooperation. And I find it actually very valuable. Yeah. Because if you just want to save, in the end, this brings your activity to reduce
so if you're a research agency, of course, you are, or even any government agency, they're interested in innovation and bringing. But if you're, let's say you're a private equity company, you've acquired some company, and many private equity companies will acquire a company with the intention that we can sell it in the next few years. And in that meantime, you have to show very high positive results. And so then there will be a lot of emphasis on cost reduction. So, there's all these aspects to it, but I think in general, whichever piece of the puzzle you're looking at, they are making decisions to maximize what's important to them. And in most cases, they have smart people trying to do that, which is not to say that they don't screw up quite often too.
It's part of the game.
Then there is, at least in the big projects, we should always distinguish what is upfront in the CapEx and what is then in the OpEx.
Yes.
And that is like the MPC solution is one that you can also bring to brownfield. And then it is actually an OpEx investment. Yes. Typically, it's just a yearly license. And then the game changes completely if you have a technology that fits even to the old products. Yeah. That's again one of the aspects why this came in the right time, in the right place, and we managed to make a product out of it.
Very true.
Other questions? So I have one actually for everybody about wrapping up. So we discussed about, let's say, transferring and maintaining a solution. So factor like to which point the things get stuck, like value creation, cost reduction, maybe large company having enough funds but not enough, let's say, agility, and on the other hand, startup having more agility but not enough funds. So what will have to happen, let's say, in working on the right problems, right, that are also, let's say, financially profitable in the long run, or there is enough motive from a company to take it over. So if you project forward in 20 years and you will be given the freedom of choosing which problem to work on and how to set it up. So in terms of collaboration, but also like having the possibility of creating more courses, for example, to train the people to maintain the solution. So how would that be? Alisa and Efe.
That's a very good question. So for me, it would be probably starting something from very low level and developing and training people to reach maturity, and then spinning it off in its own product. If that's kind of ideal scenario for me, or something that I want to achieve through my research and through collaborations and through funding, if possible, through all these stages to bring it to something independent.
Yeah, I think one thing you mentioned about the education and accessibility aspect, which also goes back to what we discussed, is really important, because like I feel like it's similar to what, when ChatGPT, they put it out, the free version, and everyone started playing, or before that the image creation and everything. People like to play with these things, but I think also there was some hype and it dies down, and some people keep using it, some people don't. So I think it's also similar in that sense. Like you have a flashy new controller, the companies may be interested, and then it goes down to sort of create sustainable solutions for automation, I think it's important that it, first of all, is easy to operate, and you have the right people in the workforce, like a little bit more ground up. Like I think right now what we have is a little bit more. We have the new technologies coming into the plant floor, like Industry 4.0. Everyone has this hype, but when you look a lot of places, it's not. It's barely 2 or 3, or there's not enough automation. So you go to a company and you say, "Oh, I have this very cool idea. Let's solve this optimization problem." They're like, "I need to model this process first." Like, I don't know. I'm based on heuristics today. So I think everyone understands the importance of these solutions for automation, but I think it's also not always well appreciated, or you don't have the right level of interaction. So I think building some sort of ecosystem where maybe it's more in all types of education, like not just electrical or mechanical, but some level of automation sort of awareness, or like these methods a little bit more from ground up, and I think that's a more sustainable solution.
Multidisciplinary.
Yes, I think the multidisciplinary aspect is quite key in that sense. So it's not just like isolated experts, but like people at least have a basic understanding of what needs to happen, so that you can build new technologies much easier, and adoption of those technologies in the field then I think would be a lot easier as well, so that you would have the people that are able to navigate the landscape easier.
Tariq?
I would hope that in 20 years we'll have moved away, or at least, well, yeah, let's even say moved away from the more or less purely capitalist model that we have today in industry and innovation, in terms of what motivates companies to do what they do, what motivates innovators, what motivates the markets, and that in the course of the next few years even, we will start to recognize that we are faced with very fundamental crises such as climate change, and we need to get together and solve these issues. And just looking at near-term financial gains is not going to do it. So that's kind of what I'm dreaming will happen, although maybe it'll be a dream, but one can have some hopes.
Thank you. Pieter, and then I think we can...
Yeah, maybe just adding one more aspect. I feel our field has become more dynamic, a bit similar to like biotech, medtech had been for a while already, that you see more startups popping up with ideas. So they're a bit more mature than I mean, traditionally we big corporation, and we have several university collaborations, and then we have an innovation funnel, and we are selecting what is good, what is bad. And now it changes, so that we see the startups. We maybe first invest a little bit in a startup. If it's something that really fits to the company, maybe we take the startup then over later. And I like that, actually, that we have become more lively somehow. It's really now a biotope.
Agile. Yeah. Good. Thanks again, everyone. I would like also to thank the speaker. This concludes the session. Thanks, everybody, for joining and for...
Thanks, Silvia.
Yeah.